So from here we see that the subsequence of a convergent sequence converges to the same limit. Okay. Now we are going to another definition, that is let x equals xn be a sequence of real numbers. X equals xn be a sequence of real numbers. Then come to the mth term. Which is the mth term of the sequence? The mth term is denoted as xm. If you can find out an nth term xm such that this xm greater than or equals xn for all n greater than or equals m. Come to the restriction. Suppose x equals xn be a sequence of real numbers. This is a sequence of real numbers. Then you can find out an nth term of that sequence, let it be xm. Satisfies this condition, xm greater than or equals xn for all n greater than or equals m. Then this xm is said to be the peak of the sequence, peak of the given sequence x. Secant xm is said to be peak of the sequence xn when xm greater than or equals xn for all n greater than or equals m. So for a decreasing sequence, consider a decreasing sequence. Consider a decreasing sequence since 1 by 2, sequence 1 by 3, 1 by 4, etc. Consider this sequence, means sequence 1 by n. Clearly we know that it's a decreasing sequence. Why? When n1 greater than n2, it is x1 less than x2 less than, x1 greater than x2 greater than x3 greater than x3. Okay. So here, sequence 1 by n is a decreasing sequence. Then we know that each of the term is a peak of the given sequence. Why? Consider the third term. What is the third term? Here x3. x3 equals 1 by 3. x3 equals 1 by 3. And what is x4? x4 equals 1 by 4. Okay. So here, suppose n, here clearly x3 greater than or equal, x3 is strictly greater than x4. For all, yes, it is n means 4 greater than 3. Okay, so again, you can find out x5. What is x5? So x3 is a peak. What is x4? If you compare it with x5, x4 is a peak. What is x5? If you compare it with the sixth term, x5 is a peak. And so on. So we know that in a decreasing sequence, every term is a peak. Okay. In a decreasing sequence, every term is a peak. Now consider another sequence. N equals, sequence 1, 2, 3, 4, etc. What is the sequence? Sequence is a strictly increasing sequence. So in an increasing sequence, it cannot be found out for all n greater than or equals 7 with a xn greater than or equals xn. There is no such a term exists. You can consider the third term. Here what is third term? Here x3. x3 equals 3. What is fourth term? Fourth term x4 equals 4. But here n, for all n greater than or equals m, it is not xm but less than x4. Okay, here for all n greater than or equals m, here xm not greater than or equals xn. So in an increasing sequence there is no peak. So this is the definition of a peak. And in decreasing sequence, each term is a peak, and in an increasing sequence, there is no peak. Okay. Now, by using this definition, we can discuss about an important theorem. The theorem is known as monotone subsequence theorem. There's a noun result, monotone subsequence theorem. Well-known result. What is monotone subsequence theorem? The theorem states that, as a statement, if x equals xn, if sequence x equals xn be a sequence of real numbers, then there is a subsequence of xn. If x equals xn be a sequence of real numbers, then there exists a subsequence of xn which is monotone. Subsequence of xn, which is monotone. Either it is monotonically increasing or it is monotonically decreasing. This is the monotone subsequence theorem. If there exists a sequence of real numbers, then there exists a subsequence which is monotone. Either it is monotonically increasing or it is monotonically decreasing. So the proof is heavily depends upon the peak. How to prove this one? That is using, the proof was done by using peak. How to define the peak? Sequence, the nth term of a sequence is that it will be peak if xn greater than or equals xn for all n greater than or equals m. And we also know that in a decreasing sequence, every term is a peak, and in an increasing sequence, there is no peak. Okay. So, here case first. Suppose there are, case first, if there exist infinitely many peaks, if there exist infinitely many peaks. Infinitely many peaks means, let xm1, xm2, xm3, etc. are the peak are infinitely many peaks, so etc. are the peaks of sequence xn. Xm is a peak of sequence xn, means xm greater than or equals xn. So xm1 be a sequence of peak of xn means this xm1 greater than or equals xn for all n greater than or equals m1. Similarly, xm2 means xm2 greater than or equals xn for all n greater than or equals m2, and so on. So this is from the definition of peak. Okay. Here we assume that the sequence xn has infinitely many peaks. What happens there? So, clearly since xm1 greater than xn, xm2 greater than or equals xn, here these are the peaks. So, clearly we have xm1 greater than or equals xm2, greater than or equals xm3, greater than or equals etc. Okay. So, let x dash equals sequence xm1, xm2, xm3, etc. Then clearly, what is this x dash? X dash is a decreasing subsequence. Decreasing subsequence of xn, so means it is monotone. So the subsequence x has a monotone subsequence, or x has a decreasing subsequence, let it be x dash. Means x dash is the monotone subsequence or monotonically decreasing subsequence of xn. Means if a sequence xn has infinitely many peaks, then here we show that, or here we can see that the sequence has a monotonically decreasing subsequence. Agreed? Why? Because if it has an infinitely many peaks, suppose these are the peaks, then xm1, xm2, xm3, etc. are the peak. Means xm1 greater than or equals xm2 when m2 greater than or equals m1. xm2 greater than or equals xm3 for m3 greater than or equals m2, and so on. Why? Because that is from the definition of peak. So clearly xm1 greater than or equals xm2 greater than or equals xm3 means it is a decreasing sequence. So means this x dash is nothing but a decreasing subsequence of xn, so that is a monotonic subsequence. That is the first case. Second case, suppose if it has infinitely many peaks, this happens. Then the case second is, if there exist only finitely many peaks, what happens? Suppose the second case is, suppose the sequence xn has finitely many peaks. So, let xm1, xm2, xm3, etc. xm are finitely many peaks, are the finitely many peaks of sequence x. Are the finitely many peaks of xn such that here clearly m1 less than m2 less than m3 less than etc. less than mr. Okay. Why? Because xm1 be a peak, then xm1 greater than or equals m2 with m2 greater than or equals m1. Okay. xm2 be a peak with respect to xm3 means xm2 greater than or equals xm3 with m3 greater than m2. So clearly m1 less than m2 less than m3 less than etc. less than M1. Put up S1 equals this MR plus 1. MR plus 1. XS1 is MR plus 1. So what about XS1? Is it a peak? No. Why? Because we assume that there exist only finitely many peaks, there are only R peaks. There is only R peaks, which are xm1, xm2, xm3, etc. xm. But if we choose if S1 is MR plus 1, surely this MR strictly less than MR plus 1. Okay, MR strictly less than MR plus 1, but XS1 or XMR plus 1 does not a peak. Why? Because there exists only finite peak. Okay. Thus there exists some S2. S2 which is greater than S1, then such that this XS1 less than XS2 or XS2 greater than or XS1 less than XS2, then clearly XS2 is not a peak, which is not a peak. Similarly, there exists S3 greater than S2 such that XS2 less than XS3, XS3 is not a peak. Means, proceeding like this, we get a subsequence X dash equals, it is XS1, XS2, XS3, etc. Then which is means these all are not peaks. XS1 is not a peak, XS2 is not a peak, XS3 is not a peak. So what about the behavior of the sequence? The behavior of the sequence is an increasing sequence. Also we already know that the increasing sequence has no peaks. This sequence has no peaks means this is an increasing sequence. So X double dash is nothing but that's a subsequence of Xn. So that's an increasing subsequence of Xn. So which is a monotone subsequence of Xn. Monotonically increasing. Thus a subsequence has if X is a subsequence, then it has monotone subsequences. Okay, so the proof is heavy depends upon the peaks. If it has infinitely many peaks, then we get an decreasing subsequence. If it has finitely many peaks, then we have an strictly increasing subsequence. Thus, if a sequence of real numbers has monotone subsequences, that is the well-known monotone subsequences theorem. Okay, thank you.